Alright, in this video we're going to begin taking a look at some of the code that will be necessary to read our Rock Band 2 controller's input. More specifically, in this video we're going to begin the concept of what we're going to call drum state. Now in the past we've gotten very used to working with things like keyboard state and gamepad state. The idea is that the state is just a struct that contains a snapshot of whatever inputs happen to be pressed at any moment that we check.
And we're going to do the same thing here?
So basically we get a state and then we can see exactly what was pressed. Now in order to make the Rock Band 2 controller easier to read, we're going to do exactly what you're saying. We're going to follow that same pattern of having a state value that we can easily check for specific button presses. The reason we want to do this is, of course, we have a lot of complicated button combinations coming in, but once we get into the game itself, it would be a lot more friendly to work with things with specific names. Like if we actually referred to the symbols as things like green cymbal and green drum, rather than their specific button combination.
And to do that, we've got to decode the input actually coming in and output it as something we can understand.
Exactly. So we're going to have this scenario where, because of this state struct we're going to put together on the inside, it'll deal with all the nitty-gritty details of button combinations. But on the outside, it's going to present an enumeration that's easy to read, discrete input by discrete input.
Okay.
So let's begin putting some of this together. We're going to jump down here in our code, in our Solution Explorer, down to our input folder, where we will add a new class, and we're going to call this class drum state. Now with this drum state, we're really going to create a struct rather than a class. I was just using the class template to quickly get some of our base usings and namespace set up. So we're actually going to change the drum state itself to be a struct, and we're going to correct our sub namespace, pull out .input. We are going to need a using statement in here as well. So we're going to have using Microsoft.xna.framework.input. Now, before we get into the actual state struct itself, we want to have some easy way of naming all of the incoming inputs from a Rock Band 2 controller. And we're going to do that by creating our own enumeration of various buttons. So we'll make an enum. We're going to call this enumeration drum buttons. And we want this enumeration to be able to describe all of the various buttons that are available. Now, looking at the controller module on the Rock Band 2 controller, we see we have dedicated buttons, things like the D-pad directions, A, B, and A, B, X, Y. We also have start and back. So we're going to need some of the standard inputs. So I'm going to jot all these down, and then we're going to do something interesting with their numerical value. So beginning from the top, we'll start with the D-pad. So we have D-pad up. We'll set that as our first value. I'll copy this D-pad up value so that we have 4 values. And that way we can express D-pad up, D-pad down, D-pad left, and D-pad right. Now, in addition to the D-pad, we also have start and back. So, jumping in here, we have an element called start, and another element called back. Then, of course, we have the standard 4 buttons A, B, X, and Y. So I'll have A, B, X, and Y. Then we get into the interesting stuff. In addition to the standard buttons, we want to be able to describe all of the actual drums as separate, discrete inputs. So let's begin with all of the drum pads, then we'll go through all of the symbols. The first drum on the kit is the red drum. So we have the red drum, we also have yellow, blue, and green drums. So next up is the yellow drum, followed by the blue drum, and finally the green drum. Now we need to address the 3 possible symbols. We'll begin with the yellow symbol, and then we'll drop down the blue symbol, and finally the green symbol. Then one last drum-related input we have is the kick pedal.
So that's a total of 18 total buttons. A total of a total. Very nice.
Now, with all these buttons, we're going to do something interesting with the numeric values. Of course, we're free to assign a specific value to each of these as we would like. So here's what we're going to do. We're going to set each value to be an increasing power of 2. So we'll start out with a value of 1 for our D-pad up. We'll double that for D-pad down, giving us 2. We'll double that again for D-pad left, giving us 4. Then 8. Then 16. Then 32. 64. 128 equals 256. 512. 1024. 2048. 4096.
8192.
8192.
16384. 32768. 65536. And then 131072. You don't have an equals there.
Ah, yes. So what's the deal with setting all of these values successive powers of 2?
Well, the cool thing is what they're going to do in binary.
Exactly. And then just to see where these are going to be used, the next one we'll do is very briefly we'll jump into our drum state struct and we'll make an unsigned integer uint called button flags. So the idea is that we're going to use each of these as different bit flags. Now what do we mean by that? Well, let's take a look at one of the properties of using powers of 2 as we increase in binary. Out to the side here in comments, I'm going to drop down a note as to what each of these would look like in binary. Now I'm only going to pad these numbers to 4 digits. Of course, we're going a lot farther than 4 digits, as you had already counted out 18 separate inputs. So, beginning with the first, a value of 1 in binary would be, if we were padding to 4, 3 zeros followed by 1. And the value 2 would be 2 zeros, so it would be 1 0. Actually, pull that line back. A value of 4 would be 1 0 0, and a value of 8 would be 1 0 0 0.
And you can see how basically what you've got here is an array of zeros where each button is kind of lighting one of those zeros up to a 1.
Exactly.
Actually, if you let me steal control from you for just a second, if we were to jump over to Photoshop, where I've got an old diagram up here from a couple of videos ago, we could represent the entire thing. Now, I could draw out 18 different slots, if you will, but I'll leave it down to 4 just for this. So let's say we have 4 zeros, but don't look at these like zeros. Look at these like LED lights that are currently switched off. What we've done is we've set up a system where internally it's just like turning one of these lights on, because that's how binary works, either on or it's off. So if we hit button D-pad up, which is our first one, it's going to be just like lighting this button, while the other ones remain off. Now, can you hit Control-Z for me?
Sure.
If we were to hit D-pad left, which is our third input, that would be just like lighting this up. The cool thing about this is if we add these numbers together, like for example, we've given D-pad left a value of 4, D-pad up a value of 1. You combine the two together, and what you get binarily is both digits actually being lit up.
Exactly.
So we've created like an internal LED table that lights up for each button that actually gets pressed.
The cool thing about that is that given that an unsigned integer is going to have 32 bits of storage that it contains, that means we can have up to 32 buttons that we can store their simultaneous state.
Right.
The idea is that we could store each one individually. We could store up to 32 simultaneous button presses or any combination thereof. So no buttons, all of the buttons hit, or any possible combination of 32 different buttons.
Which of course means you're a pretty impressive drummer with a lot of arms.
So again, just pointing out that that's the capacity we have. Granted, at this point, we're only using 18 of those possible 32 slots. But 32 does work nicely for this scenario where we have a limited number of input buttons. Now, just to show what you were drawing on the whiteboard, one more example of how this is working, because we need to describe the actual operations that we'll use to combine and separate these values. Because it's all well and good that we can have this table of LEDs all packed into a single integer, but we need to be able to, one, combine separate combinations into our single integer, and then query that integer and say, all right, out of all of the buttons, out of all of the LEDs that may or may not be lit, does the right combination for, say, the start button lit? Is the right combination for the D-pad right lit? So we're going to need to use some bitwise operations in order to pull these values out. Now, to demonstrate what we're talking about, I'm going to briefly pull up our calculator, and we'll run through just a few values. The first is combining things. So let's say we wanted to combine, let's see, D-pad up with the kick button. Actually, let me take that back. Let me do D-pad right.
Well, it's really easy in your head to just say D-pad up, which is 1, and D-pad left, which is 4. If you add the two together, you get the number 5, and that in binary would be 0, 1, 0, 1. So you can see that those two lights are actually lit up inside your system, but it's kind of harder to visualize once you get into these higher numbers.
Exactly, and that also brings up another interesting point, because if you looked at these as place values, we can simply add any of these numbers together, and all the place values will just drop together.
Right.
Now, with our case, we're actually going to use bitwise OR instead of the addition arithmetic, just in case you ever run into a scenario where, for some reason, you had multiple flags. Like, let's say you combine combination 1 and combination 2, and some of the same buttons might be lit up. We don't want to let it add 1 and 1 together.
Right.
This is all working because we're always adding a column of zeros to a single 1.
Right.
If we were using bitwise OR, we could run into a scenario where there might be multiple 1s in a given column and still total out to just 1.
Good. So this is kind of a backup plan.
Now, just to show that for the time being those values would come out the same, you're talking about D-pad up and D-pad left, so the values 1 and 4, and then those adding up to 5. We could actually see that in operation. Instead of using mathematical addition, we could use the bitwise OR operator. So what we could do is we could take the value of 1, and we could say OR the value of 4 equals, well, obviously 5. But if we switch over to binary, we see that that's 101. Nice. Or like you said, 0101 if we were padding to 4 digits.
Exactly.
So we can see that with our OR operation, that's exactly what's happening. We're just crunching these fields and combining them together.
That's right, where each place value really represents a different drum. So right there we can tell we've got 2 drums that were hit.
Exactly. Now, what if
2 buttons, I suppose.
Now, what if we wanted to do the opposite? Let's come up with another scenario. Let's actually go to the very far end of the spectrum. So jumping back over to decimal briefly, let's plug in the value for our kick. That's 131072. And let's see, what that looks like in binary. We can see that we have that 1 flag and our 18th slot as far as binary digits go. Now let's say we wanted to combine that with D-pad right. So in decimal we could say OR the value 8 for D-pad right gives us 131080, which in binary combines our 18th and our 4th bit.
Nice.
So we can see those actually building together. Now, let's say we wanted to do a check. We wanted to query this number. So looking at decimal, we want to query this number and say, all right, does the D-pad right value happen to be stored in there somewhere? Well, we can do that by using the bitwise AND operator. Of course, the idea with AND is if you take 2 bits, they must both be equal to 1 in order to come out on the other side as a 1 using AND. Meaning if you have a 0 and a 1, or a 1 and a 0, both of those conditions are going to come out to 0. So the idea is that we can kind of filter out every single flag except for the one we're looking for. And then if the one we're looking for remains after the filtering operation, then we know it was present in the overall flags. So to ask this number, if it contains D-pad right, which was 8, we could take this number and 8, and that equals 8. So that means that that flag was present.
Yep.
Now, to show that example one last time, if we had the value 131080, which again in binary, showing that we have our kick flag, our 18th place, and our D-pad right, our 4th place, so both of those are lit up. Now let's ask that number if it contains the start button value, which is a value of 16. So can we take this number and 16, we get 0.
Gotcha. Which is basically reporting back, no, you hadn't hit the start button.
Exactly. So now we can do checks and say, all right, if we run our AND operation, and that result equals the flag we were looking for, it was there. Otherwise, it was not. All right. With that out of the way, we should have everything we need to begin putting some of this code together. Now, what we're going to do in this lesson is we're just going to read out the inputs that are already dedicated. What I mean by that is we know that the kick input on the Rock Band 2 controller is completely separate. There's no combination to decode. In addition to the kick, we also have start, back, D-pad right, and D-pad left. All of these buttons are not, they don't participate in a combination of any sort. That means we can read them out directly without really decoding them.
Okay.
So we're going to use these buttons to get our initial code here in drum state set up. since this is a very simple check where we can begin assembling our button flags. And then we'll come back in a later video and put our more complex decoding logic in place. So what we want to do is do a series of if statements, checking for various incoming buttons, and then we want to set the appropriate drum button flag for each incoming gamepad button. Now also the way we're going to set this drum state to work is it's actually going to be dependent on gamepad state. Rather than try and dig into the more low-level point at which the X input for XNA works, which we technically don't even really have access to through the given interface. We're just going to rely on the gamepad itself, read out the raw buttons, and convert those over to our buttons. So the way we'll do that is in order to treat the state like gamepad state and like keyboard state. The idea is that the moment when we want to decode something, we will do so by creating a new drum state struct, and then we'll feed in a gamepad struct to use as a basis. What that means here inside of the struct itself is we're going to have a public constructor, so public drum state, and we will take in a gamepad state, which we'll simply call pad state. So the idea is that we can see any combination of gamepad buttons, and then it's up to us inside of this constructor to read and decode all of the inputs present and then store them in our button flags integer. So, again, beginning with the simple buttons that can be read out individually, the first of which is the kick button. That's represented by the gamepad left shoulder button. So we'll put together a simple if statement saying if pad state dot is button down, and we'll feed in buttons dot left shoulder. If left shoulder is currently pressed, then we want to register that flag inside of the button flags integer. We'll do that by saying that button flags will be equal to, so we want to OR this to combine it. We'll use the single pipe symbol for bitwise OR. We'll say it's actually going to be OR equal to the integer value of our kick button. So looking back up here at drum buttons, we can of course read from this enumeration and find any of these values we would like. So if we want to gain the kick value, we could access drum buttons dot kick. Now of course to store this as an integer we do need to cast, so we'll cast this over to a uint. And correct a little bit of spelling, and everything should be happy. So that's the idea of numerically storing the kick value into our button flags. Also, as soon as we get into the constructor, I do want to make sure that we explicitly set button flags to 0 to satisfy the requirement of the struct's constructor that all fields be set up upon initialization. So, really that's all we need to do. This is simply translating the gamepad button left shoulder to the drum button kick. Of course, button flags is just a number, so we cast to uint before storing. Now let's do the same thing for the remaining buttons. The next button up is the start button, so we're going to copy these two lines of code and duplicate them so that we can drop in drum buttons, or excuse me, gamepad buttons dot start. The start button is going to map directly to the drum buttons version of start. So we'll simply set button flags. We'll combine button flags with the value in start, so we add that to the list of fields that are currently set. Now we need to do the same thing for the back button, so buttons.back will be stored as drum buttons.back. Then we have two more values, d-pad right and left, so that is buttons.dpad right we will store as drum buttons.dpad right. And finally, buttons.dpad left will be stored as drum buttons.dpad left. Alright, so all these buttons should now get taken in and stored. Now there's a few more methods we want to add to our drum state struct. We would still like the struct to behave much like gamepad state, where we have the methods is button down and is button up. So we can ask the state whether or not a specific button of interest is pressed or not. So we're going to do the same thing here with a few methods. We'll make two public methods. They're both going to return a Boolean value. The first is going to be called is button down. And then we'll pass in the drum button of interest that we would like to check. So we pass in a drum buttons parameter called button. Now, again, we're checking to see if a specific button is currently pressed. And as we had just demonstrated inside of the calculator, we can see that we can check for the presence of a button by taking the overall flags field, button flags, and then performing an AND operation against the flag we want to check. That result happens to be the flag, then we have found the button we want. So what we're going to do is, in order to make the AND operation a little bit more clear, we'll first cast this button over to an integer, an unsigned int, and that'll make it easier when we do all of the math. That way we don't have to cast in line. So we'll make a uint variable called button flag, and that will be equal to the uint cast of button. So basically we have now it's just a number, button. We have another number, button flags, and we'll check for the presence of button. So all we're going to do is check and see if button flags and button flag is equal to button flag. Now we need to change this around a little bit for order precedence, since right now equals is taking precedence over our bitwise AND. So we're going to drop the AND section into parentheses. So we get this result and see if it happens to equal button flag. If so, button flag was present in button flags, and that means that our comparison operator is going to return true. Now, since the comparison operator itself is a Boolean value, we don't have to worry about using this with an if statement. We can simply return the overall expression. So we should be able to just return the result of this expression directly. Since again, this comparison operator is going to say, okay, true if button flag was equal to this operation, false otherwise. So now we can do the same thing, roughly, for is button up. So what I'm going to do is I'm going to copy the whole method, paste it to duplicate it, and change the method name to is button up. So now I want to test the opposite condition. We're still going to take in a drum button parameter, still going to cast it over to a variable called button flag, still going to do a bitwise AND operation against it, but this time we're going to return the inverse. We're going to say if is not equal to button flag. So the idea here is that, let's say button flag was not in flags, was not found, that means the result of this operation would be 0 or would be not equal to button flag. But in that case, if it's not equal, then is not equal to operator would return true, the opposite value, and return. So again, same operation, just changing the return rather the comparison being used. Now, with that, we at this point in time don't have a place to test this code. This drum state is meant to be part of an actual dedicated drum input class, which we have yet to code. We have, however, covered the concept that's used for storing these buttons and assembled everything, so all of our code is at this point ready to go. We can build, everything gets saved, and we see that there's no errors in the code. No syntax errors anyway. So with that, that's going to wrap up this video, and in the next video we'll progress on to the input class.